Right, so we left off with calculating limiting reactants in solution. So the general premise is, once the pen works, turn on, okay. So the general premise is, you know that when you mix two solutions, it's very possible you will get a precipitate form. You have seen this in lab before. Now there are some times where there is not a precipitate forming, and that's okay. But if there is not a precipitate forming, then there's no problem to be had here. So we're going to only consider solutions that when we mix them together, we get a solid precipitate. Okay, so the trick is this. When I mix these two solutions, whatever molarity they were initially, you need to understand that upon mixing, their molarities, everything, all the molarities will change. And the first reason why the molarities would change is because now you have a new total volume, right? If you know molarity is moles per liter, let's say I had 10 milliliters and 10 milliliters added together. Well, the total volume is now 20 milliliters, right? So the new molarity has to be recalculated. Does that make sense? Right? If I said, what is the concentration of ions? The second reason is if there is a precipitate, some of those moles are going to turn to solid and no longer be dissolved in solution, which means you do not have the same number of moles dissolved, so you have to recalculate what those molarities are as well. So here is the listing of steps, but rather I'm going to move on to the next page, and we're just going to do an example because that's probably the best way to learn. And I would, at this point, I advise you to insert a page here because this is a lot of writing for these types of problems. Okay. So we're going to do this, for example. I was just testing my Apple battery earlier. Okay. So we're going to try this problem that starts right here. All right. And the first thing, of course, is you need to balance the equation. So what do we have? We are combining lead nitrate with aluminum sulfate. All right. So lead nitrate, lead, the charge of +2. Nitrate is a -1, so there's lead nitrate. If you are working with solutions, then your state is aqueous because it's starting as a solution. And we get aluminum sulfate is the other reactant. Always check your charges, right? Don't just write AlSO4. That's not right. You have to check your charges, make sure that your compound makes sense. And you are told that lead 2 sulfate precipitates. So that is your solid, right? Precipitates means solids form. So we use S as our solid. And then we have our other reactant. By the way, you guys recognize this pattern. What type of reaction would this be classified as? Remember the different types? This is a double replacement, yes. So if we know that lead nitrate or lead sulfate is the solid precipitate, then the other ions would be our other product, which would be aluminum and nitrate. And nitrate has a charge of -1, aluminum's a +3, so therefore AlNO3 3. All right, let's balance this. I'm going to balance starting with the aluminum sulfate on the left. So if we've got 2 of these here, let's put a 2 in front of here. That means I've got 6 nitrates on the right, so I'll put a 3 here. And that means I need 3 leads on the right, so I put 3 here. And that's 3 sulfates. Okay, we are balanced. All right, first step, balance your equation. Okay, so a solution reaction problem is a limiting reactant problem. At least that's how it starts. Okay, so we have volumes and molarities. The first thing we need to do, of course, by default, should be automatic by now. Moles. We got to find moles. Okay, so what do we know? We know that we have, and remember, whenever I write liters, whenever I have volumes of solutions, I always write them in terms of liters because it's liters that has to be multiplied by molarity. So for the lead nitrate, switch colors here, we've got 0.015 liters multiplied by 0.11 molar, and I write molarity as moles per liter, just to make it visually obvious that the liters cancel. All right, so 0.00165 moles of lead nitrate. And try to write small. Try not, if you have big, bubbly writing, try to curtail that a little bit, because these are the types of problems that end up taking a lot of space as you go from left to right. And always try to start leftmost, as far leftmost as possible, because you'll be going all the way across. All right, so we're going to do the same thing. We need moles of the other reactant, aluminum sulfate. So aluminum sulfate, we've got 0.012 liters of 0.2 molar. Okay, so 0.0024. The nice thing about notability is the color coordination is pretty easy, right? It makes things stand out. Moles of aluminum sulfate. Okay, I've got the moles of each reactant. That is the first step. So the goal of this type of problem is to find the concentration of all 4 ions. Now let me take a backward step here and kind of point out, what are my 4 ions? The 4 ions in total are going to be the lead ion, the nitrate ion, the aluminum ion, and the sulfate ion. These are the 4 ions in question. Ultimately, this is our goal, to find the molarities of these. But because there is a reaction taking place, the first thing that I need to solve for the yield is of the precipitate. So I'm going to continue on like a limiting reactant problem and solve for the yield of lead sulfate, because that was identified as the precipitate. So, mole ratio, 3 moles PbSO4, and I need to cancel the lead nitrate here, so 3 moles of PbNO3 2. Okay, so the 3's obviously cancel, the units cancel, and so 0.00165 moles of PbSO4. That's what's expected from the first reactant. Let's do this again for the second reactant. 3 moles of PbSO4 over, the coefficient on aluminum sulfate is 1. Okay, so 0.0072. All right, decision time. Which of these is my theoretical yield? Yeah, the lower. Theoretical yield. And by identifying our theoretical yield, by default, that allows us to identify the limiting reactant. The limiting reactant is the lead nitrate. Okay, remember they both come from the same line of work. This number is irrelevant. Scratch it off, so it's out of the picture. All right. So I've identified the theoretical yield. I've identified the limiting reactant. Okay, so I'm going to make a little chart off to the side for my ions. And I'm going to work through these one by one. Okay? Now, the first thing I would say is look closely at your theoretical yield. And then look closely at the limiting reactant. What do they have in common? Lead. Lead is in your solid precipitate, and lead was in your limiting reactant. Okay, so to point that out here. So what that really tells us then is lead was truly the limiting reactant. Lead was completely consumed. And so if lead is what's limiting the amount of solid precipitate you can make, and the reaction stops because you ran out of lead, well, how many moles of lead do you have floating around in solution at the end? None. So the molarity of lead is 0 because it was literally the limiting reactant. Okay, so I may have gone over that too quickly, guys. When you get to this point, once you figure out the theoretical yield, you need to look at the formula of the theoretical yield and the formula of the limiting reactant. Right? The formulas here and here. And you should identify a common ion between them. Whichever ion is common to both this and this, that is what there will be none of at the end. Okay? All right. So, now, looking back at our balanced equation, since we identified lead sulfate as the precipitate solid right here, right? We said that's our precipitate, that's solid. Well, what state is the aluminum nitrate in, guys? It is aqueous. Okay, so if aluminum nitrate is aqueous, that means this started as a solution. The aluminums were in solution, the nitrates were in solution, and they end in solution. They were not involved in making your solid product at all. So how many moles of aluminum or how many moles of nitrate were consumed? 0, none, right? So in other words, your moles of those ions did not change. Okay, because they did not precipitate or participate, we're going to call them spectator ions. They just kind of hung around and watched. The spectator ions were the aluminum and the nitrate. Moles were unchanged. Okay, so the moles were unchanged, but we still have to figure out how many moles there are. And that's not too hard, because in order to do that, we just take the initial moles. So let's say for aluminum, all right? I'm going to use color. We're going to use green for aluminum. Notice that we started this problem with 0.0024 moles of aluminum sulfate. Okay? At the start. I can't spell start. At the start. Okay? At the start. S-T-A-R-T. Okay. Everybody okay with where I got that from? All right. I'm going to just stoich this out to solve literally for the moles of aluminum. In 1 mole of the aluminum sulfate, you should recognize that there are 2 moles of aluminum within. Okay, so what that means is individually there was 0.0048 moles of aluminum ion. Now, like we said, with spectator ions, the moles do not change. What we did here in green was we just figured out how many moles of aluminum there were at the beginning. That is also how many moles of aluminum there are at the end. So if I said, what is the molarity at the end? Molarity is just moles divided by volume. We have a cumulative volume, and all we have to do is add up our total milliliters, right? What do we got? 15 and 12, so our total volume is 27 milliliters. So in other words, the molarity of aluminum is equal to 0.0048 moles divided by 0.027 liters. Which is going to be, I'm going to write that here into the box, 0.1, after rounding, 0.18 molar. I guess I'll write it here too, 0.18. Okay, let's pause here. Let's follow steps, make sure we're all caught up, we all understand what happened. I took the beginning moles of aluminum sulfate, and I just canceled the aluminum sulfate so I can solve for this in terms of moles of aluminum. Once I had moles of aluminum, I could find the molarity of aluminum. And this is all possible because I knew the aluminum did not react. All right, let's do the same process for nitrate. I'll use blue for nitrate. So I need to find the beginning moles of our source of nitrate. Guys, can you tell me what number is the value for our beginning moles of nitrate, of the nitrate-containing compound? Yeah, 0.00165, yes. 0.00165 moles of lead nitrate at the start. Okay, I'm primarily concerned right now with nitrate, so I'm going to stoich this out. I know there's 2 nitrates for every lead nitrate formula. So 0.00165 times 2, 0.0033. I don't know why I used the calculator for that. I probably didn't need to. Okay, moles of nitrate. All right. Our total volume is the same for all ions because they're all in the same test tube. So molarity of nitrate is equal to 0.0033 moles over 0.027 liters. .12 repeating, so our nitrate is 0.12 molar. You guys still with me? Okay. Question, Ron?
When it says like calculate the molarity before mixing, would you use the molarity like when they're originally in the solutions, or when they're like poured together but the reaction hasn't occurred?
Does it say that here?
So like when it says calculate the molarities of all 4 ions before and after mixing.
Oh, okay. So before, it's kind of silly for me to ask of it before, because before the molarity is already labeled on the bottle, right? So before the molarity before mixing would be whatever the molarity is times whatever subscript that element has. Okay. You know what though? That's kind of a silly question, to be honest. I don't really care about what the molarity is before. I'm really mostly interested in what it is after. Okay. But good question. Yes. Yeah, so you have to apply the subscript to account for the molarity of that individual ion. All right. So what's left, guys? What are we missing? Sulfate. There's a term for the sulfate. If we have identified the limiting reactant, yeah, sulfate, it would be, man, what color did I not use yet here? Did you know I went a whole year without knowing you could change like the color palette options? Like I didn't know this second palette here existed. Let's see, let's go with a tangerine. All right. Okay, so here's the thing. Remember from last lecture that whenever you need to solve for the excess reactant, you need to start with this value. What value is it? In order to find the excess reactant, you have to begin with this particular value that you found, the theoretical yield. Okay, so to find the excess reactant in solution. So the excess, or the theoretical yield, is 0.00165 moles of PbSO4. Everybody see where we got that earlier? Okay, so my focus right now is on the sulfate. It's the sulfate I'm trying to find right now. So what I have to do is I need to use the theoretical yield and solve for how many moles of sulfate were actually used. So, let's use mole ratio from our equation. The ratio is the sulfate containing compound was aluminum sulfate. So for every 1 mole of aluminum sulfate, there were 3 moles of lead sulfate produced. Okay, so 0.00165 divided by 3, which is going to be 0.00055 moles of aluminum sulfate used. Okay, that's how many moles of aluminum sulfate were used. If only I knew how many moles of aluminum sulfate we began with. Do I?
Yeah.
Yeah, I do. What is it? Right. If it's from earlier, guys, it's right here, right? We started here. This is one of the first things we calculated. We know that's how much aluminum sulfate that we began with. So 0.0024 moles at the start minus 0.00055 moles used will tell us what remains. Which is 0.00185 moles of aluminum sulfate excess. Okay, we're almost there. So remember, my goal is to find the molarity of the 4 individual ions. Currently, I figured out the moles of the compound aluminum sulfate that are excess. I'm not interested in the compound as a whole. I'm only interested in the ions specifically. So what do I do to tweak this so that I'm solving for just the ion? Stoichiometric ratio, yeah. There are 3 moles of sulfate within the aluminum sulfate formula. So 0.00185 times 3, 0.00555 moles of sulfate are excess, and I have one more thing to do before I complete my table of molarities. What do I need to do with this number? Divided by the volume, yes. So 0.21 molar. And we have now completed the problem. We have all 4 concentrations for our 4 ions. So this problem is a limiting reactant problem set in solution. And when you're talking about problems that are set in solution, these ions, you treat them independently because these compounds, they separate and float around independently in solution. The only exception to that is the precipitate, which clumps together. Okay. How are we doing on that? Can we do one on our own? I guess that was a rhetorical question. We're going to do it anyways, right? So I guess we'll find out. Okay, so what I'm going to do is I'm going to stop this video so the people watching don't have to sit through us waiting for you to do this. So